Everyone, this is my Lab 3, Black Hole and Orbits. And to start, the purpose of this lab experiment in Part 1 was to determine the mass of the black hole from analyzing the star's motion around the black hole. And then in Part 2, the purpose was to simulate the motion of a spaceship in a figure 8 motion around a planet and moon system, determining the value for the initial velocity that will not cause the spaceship to crash using the guess and check method. And the result of this experiment, we were able to find that the mass of the black hole was estimated to be 8.47 times 10 to the 94th kilograms, and then the spaceship was unable to have a figure 8 trajectory, but I did get it to not crash into the planet or the moon when I had it starting with an initial velocity of negative 29,000, 26,000, 0. And then some key concepts to look at when doing this experiment is Newton's second law, which includes like the velocity update formula and the position update formula, along with the fact that F net equals dp dt, which will be important in our code. And then we also have F net perpendicular and parallel, and it's important to note that the net force total is equal to F net parallel plus F net perpendicular. And we also look at the gravitational force as we're not working in the Earth's gravitational system, so we use the formula Fg equals negative g m1 m2 over r squared, where g is the gravitational constant, and then we have the masses of the two objects we're looking at and the distance in between them. Part 1, starting with my initial conditions, where we have the gravitational constant, the mass of the star, delta t, and we didn't really change much with this, with calculating the velocity from the data. And then looking at the while loop, we started by using the velocity components from the initial conditions to calculate or make a variable for the initial and final velocities, and with those we're able to compute the initial and final momentum vectors. And once we have all that, we're able to calculate the star's change in velocity as well as the change in momentum, and using this we can calculate the change dp dt. And then using Newton's second law to calculate F net, we really just have to set the net force equal to dp dt, as according to Newton's law they equal to each other. And then really we just use the same calculation method for the parallel component and the perpendicular component, as you can see in the code shown, and then we just set F net perpendicular equal to dp dt perp, and the parallel set to the parallel. And then with all this we were able to calculate the mass of the black hole with the equations seen below. Here's my model from part 1 with the estimated mass of the black hole, the magnitude of the force in the perpendicular direction as well as the force in the parallel direction. And for the system, I said it was the star, and the surrounding is the black hole, space, and really anything else that might be acting on the star. And now looking at part 2 with the code, we have the initial conditions as the gravitational constant again, the mass of this planet, the mass of the moon, mass of the ship, and delta t, which we did not change anything in these 6 lines. And then we also have more initial conditions for the moon, and really in the initial conditions what we changed was for the spaceship, which was the initial velocities that we changed with the guess and check method, and I put that the speed in the x direction was negative 29,000 and in the y direction it was 26,000. And then we look at the while loop, where we first started with finding the force acting on the moon in the system using the equations that you see below, and then after that we calculated the net force acting on the spaceship. And from having both of those figured out, we were able to apply Newton's second law and the position update formula using the velocity that we were guessing for in the initial conditions to run our code and see if the orbit would complete or not. And here's my model from part 2, where it did complete, but it didn't make a figure 8. I have my initial velocity listed, and I put the system as the spaceship, the planet, the moon, and the surrounding was nothing. And some possible errors from this could be that the wrong initial velocity was guessed to make the correct shape, which is possible as it was guess and check, and then assuming no forces were in the surrounding. And for the discussion, what does it mean? So how are the net force and its parallel components different from the rate of change of momentum? So mathematically they are the same, as according to Newton's second law, the net force is equal to the rate of change of momentum. Essentially, the net force is the cause for the change, and the change in the momentum is the effect, but they're really mathematically the same values, and this is really the same for the parallel net force component causes a parallel change, and the perp component causes a perpendicular change. And then what if? So this imaginary system has a black hole, a star, a planet, and a moon. If you wanted to predict the motion of the entire system, what would you need to include in your comp model? So you would really need to account for all the interactions in the system between the black hole, the star, the planet, and the moon. Additionally, anything in the surrounding that may be acting on the system also must be included. And a dominant force would be the gravitational force that's acting between each entity, and it would be dominated by the most massive body. And overall, I was successful in finding the mass and also having an orbit around the planet. It just wasn't a figure 8 shape. Thank you.